So, hello, welcome to another episode of Flying High with Flutter. I'm your host again, Alan Wyma, and today we have another Manning author on our show. We have Emmanuel, the author of AI Pocketbook, the AI Pocketbook. As I was saying before the show, this book really spoke to me because it was something I've been looking for. Because the whole AI field itself is quite massive, especially if you start going into verticals. And your book was like something that I've been wanting for because most of the materials I've been looking for have been a little bit too specific, and yours kind of goes somewhat shallow, but also sometimes pretty deep on specific areas. And and that's been exactly what I'm looking for. And you've even provided references of other other things I can get into some more. Like specifically, you said, okay, this is like the source code for, I think it was ChatGPT 2, I believe you listed, and also you have I believe it's OpenAI has like how they tokenize, which is quite interesting.
Yeah.
So like I had no idea that these were actually available, and this is stuff that, because for me it's like I want to know like what is this stuff? Like for instance, like what is HTTPS? Okay, secure, but how is it secure? How does that work? What is the cipher? I can start asking more deeper questions that get into it, and your book is like similar to this kind of flow. But at the same time, it's like if you want to know, here it is. We're not going to get into it, but here and that's really a great reference. So I think this is probably one of the first books I'll actually like. Maybe I'm going to go home tonight and actually just keep reading because it's been fantastic experience. Sorry to keep not blowing smoke, but what's the right way? I just keep giving you praise, I guess I could say, because it's been really a great book.
I really appreciate this, and I'm very happy to hear that. And striking or finding a point between being a little bit too detailed or too shallow, that's the hardest thing to do when you write a book. And I'm glad to hear that it's working well for you. And this is why AI can't actually write a book, because the difficult part is not the writing itself, is this thing that you're saying. I decided not to explain certain things, and then I provide you with a link where you can go and learn more, right? That decision, it's almost an editorial decision based on who you think your audience is and what you think they want, right? And I'm glad it's working for you, but that was the hard part, to also decide what not to say, what are the things that, and it's a field that's going to change a lot. So I thought we need to cover the foundations very well at a level where you know what's going on, but then you'll be able to go and learn more, especially as things change. That was my my idea. And I was approached by Manning because they wanted to write a survivor's guide to AI, right, for software developers. And I told myself, what is that? If I, and I've been working with junior software developers or people who've learned software development but not AI. And I was thinking, okay, what would I want to know if I was one of those people, right? And I wrote that book for them essentially, and hopefully, it's doing the job.
Yeah, I think so. At least for me. So this episode's probably going to be a little bit more different because we're going to be focusing more like on AI itself, which I think is something that is good to take a look at, because as you're writing code, you're going to be actually working with things like Cursor or other kinds of tools that can help you to actually write code. But I think it's good to start to understand like how do I say this? What is actually happening under the hood? Even at a high level, it's really important to understand, because sometimes I've been using GitHub Copilot just recently because I'm using VS Code mostly. And it's been guessing stuff, but not 100% exactly what I want. But sometimes it does. And I'm actually kind of curious if it's reading or listening to myself like talking out loud, because sometimes I talk out loud and I'm like, oh yeah, I need to use. So for instance, I'm actually using, like when I'm using CSS, I have some like predefined value somewhere. And so I reference like, okay, this component's going to be using this one. And I have it so that way I can swap that like existing reference. So it's like, okay, I have border XX, border width of medium, and I have that defined somewhere. And I say, okay, the border of this component's a different CSS thing, and it points to this one. I can easily swap it out with something else. And so I'm saying it out loud. And I also have designed another window, but it's like it sometimes is able to predict exactly what I want. I'm not sure if it's predicting
Right.
or if it's like reading something. It's getting kind of creepy sometimes. Sometimes it's too accurate and it kind of freaks me out. But sometimes it's like way off where it's like I'm writing some code and like I want to write, yeah, again, like it could be a specific CSS class, and it just adds in all this extra crap which I don't want or don't need. And sometimes it's
Yeah.
exactly what I want, and it's good to understand like what's going on. And you go over quite a few things in here. I didn't get to the hallucination part, which is probably some of that, but you do talk about temperature, which is quite interesting. But
Mhm.
before we get into that, right, let's kind of talk a little bit more about you. So Manning reached out to you, so that means you have to be some kind of authority, no? Like, do you mind to kind of talk about like, yeah, who are you, kind of your history with? I'm not sure exactly what your background is, but whatever that background is, since we
Yeah,
didn't get to that part
of course.
up until
Yeah.
till
So
now.
I'm a software developer in the first place. I studied a mix of computer science and software engineering, I would say. And then when I finished that, I landed by accident on a PhD in AI. This was a while ago, before the ChatGPT era. And I studied image analysis with AI in my PhD. And this was early days in the field I was working in. That was satellite image analysis. So I tried to use AI to outline shapes in like buildings or cars or roads that are seen from satellites or planes. And I kind of didn't want to continue working in research at that time. I wanted to do something more commercial where you build a product that is used, and that's really, really a product that works. And I became a data scientist at that point, which was the natural transition for people working in research, especially with an AI background. And data science at that time, we're talking, this was almost 10 years. It was like 2017, 2016. People said, if you know anything about AI, if you have a mathematical background, go and work in data science, which means we're going to be using AI to help businesses with, recommendation algorithms, with understanding customer behavior, with predictive maintenance, predicting when a piece of an airplane will need replacement and stuff like that. So we had all these people trying to use AI for all sorts of commercial applications. I was quite disappointed very on, and that was pretty pivotal in my career, I would say, because I witnessed a lot of overhyped, AI projects and a lot of failed AI projects. And I just thought people are overestimating the power of AI. They are making always the same mistake, which is to launch an AI based product or project because everyone says AI is so cool. Not because you know your customer or you understand what the problem is, or you don't even try to find the best way to solve the problem. So you just push AI everywhere. And I saw that so much. And that led me to my first book, which is called Smart Until It's Dumb, where I kind of, if you want, expose all this dark side of the AI industry. And let me tell you, I wrote the book before ChatGPT was launched. Almost, I almost finished the book when ChatGPT was launched. So I was saying that there's a bubble in AI, right? And that was before ChatGPT. Then, because ChatGPT was launched, I added more examples to the book, and then it was launched. And I think the thesis of the book remains intact nowadays. This idea of AI being misunderstood, right? Which is one of the things I am fighting against. And and when this whole ChatGPT thing happened afterward, I kept speaking to people and to lots of companies to understand what was happening. And that's when Manning told me we need to a book on how to survive this. And I've been helping lots of companies build products. You know, I've advised lots of companies on the commercial side of things. When you combine technology and business, you think, is this feasible commercially? And I feel like being in the middle is quite interesting because a lot of business people, they promise something, right? With AI, but then there's a limitation that they don't understand because they're business people, they're not technical people, right? And it is a great position to be in as a technical person, to be the one evaluating this promise, you know, in terms of technical / business feasibility. Is this going to actually do what you promised or not? What do we do about hallucinations? Um, yeah. So essentially, I've been commenting on AI for a while and other things. So that's my career. You know, I keep working as a software developer, so I do write software. As a I have a part-time developer job, and the rest of the time I'm speaking with people about AI. I am writing books. I am learning what entrepreneurs are doing. I am learning a lot about all these failed AI projects that nobody ever talks about. So yeah, that's kind of a that was an intro, about me.
Yeah, thanks for letting me know about your book because I like this one a lot. I did went ahead and favorited your book on Amazon, so I may pick up a copy. Is it written in the same style as the one you read for here, or probably a little bit different? The one
It's a
about
bit
smart
different.
system. Mm-hmm.
So it's a bit different because it's a general nonfiction book. So it doesn't target specifically software developers. It's more of there's even a whole chapter on consciousness and the mind.
Mm.
And the reason I wrote that is, and it's actually relevant, I think, to software developers, because we get this a lot of we're building artificial brains, or neural networks just work like neurons, and I wanted to say, no, that's not quite right. We don't even understand how neurons work. So I did research on that, and I kind of wanted to pop that bubble. I even discovered interesting things. So, for example, the original paper on convolutional neural networks that was published like 20 years ago, it didn't relate neural networks or convolutional neural networks with the brain at all. Right? The author said this is a technique to process images based on how we think images should be processed, blah, blah, blah. But then it became a really good marketing tool to say that it was imitating the neocortex of the brain and how our neurons process visual inputs, right? So in that book, I wanted to kind of pop the bubble a little bit from every angle and say, let's get realistic about AI. But it could be a good compliment, the book. Yeah, I think you should give it a go. Yeah.
I mean, of course, if I'm picking up more of your work, of course you're going to say, yeah, it's great. But I guess maybe the main question I ask is it okay to pick it up as like an audiobook, or do you think I should sit down and read it? I guess audio should be okay. I mean, with the AI Pocketbook, you have links that I should follow up on. I think it requires a bit more work because I like to
Yeah,
usually listen to
exactly.
audiobooks when I'm at the
My
gym. But yeah,
my other books are great for the gym. Yeah, as audiobooks. They have almost no pictures. You can just listen to it. Yeah. People have been enjoying the audiobook version a lot. Yeah.
okay.
So, and I do the same. I listen to audiobooks at the gym, and I understand where you're coming from. And I think Smart Until It's Dumb is a good audiobook. Yeah.
All right, it's already favored. I think I have a because that was the question. I always had like all these Audible credits, and because I think I subscribe and get like 12 a year. I think I'm about to have a new cycle soon, so it's on the list
Good.
already. Look forward to checking it out. Um,
Yeah.
yeah. So as I was talking about before, this book really kind of speaks to me a lot, and I was getting into it, and I'd like to talk a little bit about. I mean, the first chapter itself, I think, is just something we could probably spend the whole episode on already enough because there's a lot of information there. Especially if
Mm-hmm.
you have a PhD, that means you can actually kind of get a little bit deeper on this stuff. What I'm actually
Mm-hmm.
kind of curious about, or actually, let's do it this way because I'm guessing there's people out there who don't really know what's going on. They type something into the prompt and they get back an answer, and then they're kind of like, okay, that's makes sense. But there's a lot underneath the hood, and I'd like to kind of talk about some of those kind of basic glossary words. And I think the key ones to talk about is definitely tokens. What's a token, and why should I
Mm-hmm.
care? What's the context window and how it relates to the tokens? Because I believe they're highly related. I believe you get context window from the tokens. Again, you're the master. I was just reading it today. I feel like I'm a genius because I'm like I can talk about this stuff because I just started reading the first chapter. But I would love for you to kind of talk about this to make sure I got it all down properly, and also talk a little bit more about like the embedding, right? Which is something I've actually
Yeah.
never heard of before. So I'd love to hear more
Yeah. Which
about that
is
because like I'm
very
very
important.
curious about
Yeah.
how it actually works and then how that embedding actually. I mean, I think all this stuff basically, you understand already like what I'm looking at. Like that's basically the pipeline. Once you type into the prompt, you get back the
Yeah.
output. There's a lot of in betweens that are happening. Do you mind to kind of go over
Yeah.
that
Let's
process?
let's
I think there's
yeah,
a lot of
absolutely.
interesting stuff there.
Let's take it one step at a time. First, what is an LLM, like a language model, right? Because that's what's under the hood powering this whole thing. And one of the things I like to explain first is that ChatGPT is not an LLM. So it's an app that uses an LLM, right? The LLM is under the hood, and ChatGPT does other things that we could call tricks to enhance the functionality of the LLM. The LLM is a language model. It's a computer program that tries to represent language, how language is structured. And its main objective is to predict the next word, or more specifically, a token, but we can talk about that in a second. We can think of it as a machine that predicts the next word. So if you say the Eiffel Tower is in, then the next word is probably going to be Paris. And that's literally what the LLM does. It creates a model of the language to be able to predict the next word. And then, but how come when we use ChatGPT, or like you were saying, Copilot, when you're coding, why does it produce entire sentences? Well, because the outer wrapper that uses this LLM uses a trick, which is to get the LLM to eat its own output, right? So you get the LLM to produce one word, you attach that word to the original prompt, then you use the LLM again to produce another word, and then you attach it again, right? So the LLM is used repeatedly to produce entire sentences. So that's one of the tricks that are used to augment what the LLM does, right? And another question could be, how does the LLM know when to stop, right? Or how does the LLM wrapper know when to stop doing this? Well, there's a code word that the LLM is trained to output, which means this is the end. This is the end of the sentence. I predict that, the best thing that would come next, the next word, is just this code word that says we're done. You can imagine that when you finish yours sincerely, a name, then the most logical follow-up is to just finish, right? And that's when the LLM outputs that code word, then the outer wrapper stops producing text. Right? So what I'm trying to say here is that there are lots of tricks to turn a machine just designed to produce the next word into something a lot more powerful. And then the other thing that this outer wrapper does is it inserts lots of things sometimes. Like it can perform a search. You can imagine a Google search and collect the results and put that into your prompt without you, the user, knowing it, right? That happens all the time. And this is happening all the time when you're coding, right? Other files from your project are inputted into the LLM, right? And the lots of things are happening. We can even see functions being called, like little pieces of code being called by the LLM wrapper. When you ask a complicated question, like a mathematical question, then maybe they will, produce a little program. They will execute the code. This is not happening inside the LLM, right? It's all outside. And then when it produces a results, the LLM wrapper will put that into your prompt. You don't see that as the user because your prompt, you believe, is your prompt, but your prompt is all the time being altered. There's also this new generation of reasoning AI, as they call it. That's a little bit of a publicity stunt in reality, because what this does is essentially add instructions to your prompt that tell the LLM, please produce a list of steps of how to do this, before actually doing it, because people have observed that it works better. But all of this stuff is hidden from you, the user, right? So all of this story is to tell you that an LLM, a thing that produces the next word, it tries to guess the next word based on the previous words. And then the LLM wrapper, like ChatGPT, is a whole full-on app that does lots of things and uses the LLM. So that's where I wanted to take you first before we speak of tokens. What do you think? tell me if you have any questions. Then we can move to the tokens. Otherwise,
No, I think that's definitely a good point because I never really thought about that. Like when I read your book, it's like, okay, it's cannibalizing up until it says, okay, done. So that's, I mean, because you're not going to see that recursion happening. I mean, it
no.
happens too fast, and also it just spits out the very end at you. So that's pretty important to understand because it is a question. It's like, well, how does it know what's next? And so it literally is like recursing. So that's a great point.
Mhm.
I don't have
Yeah.
any questions about that. That makes a lot of sense to me.
Yeah. Cool. Let's move on to tokens, which is another word you mentioned. Ideally, we would want to use individual letters as an input, to an LLM because they're kind of very fine-grained, but that doesn't work very well. We're going to speak about why in a second, but you want to input meaningful things one at a time. And you want the LLM to output meaningful things. And a word is a meaningful thing. Like I said before, the Eiffel Tower is in. You can split that into words, and then ideally the LLM will output Paris in one single go, right? So what the LLM does is it actually picks words from a vocabulary of about 100,000 words every time. But not every word is going to be in that dictionary or that vocabulary. So what the vocabulary has is also common pieces of words like ish, right? Or ly, like ly, and that lets the LLM produce words by combining common pieces of words, right? And also in this vocabulary, there are individual letters too, which means that if a word does not exist at all in the dictionary that the LLM has, it can still put it together by combining letters, right? And these units are called tokens, which token essentially means a word or a common piece of a word, or worst case scenario, a letter, right? So that's why people speak of tokens a lot, because saying words is not quite accurate. You'll see that your input is not split into words one by one sometimes. If you say, I'm hungry-ish, it will be split into hungry and ish. And those will be two tokens that will be inputted into the LLM. And LLMs are billed by the token, right? So the more tokens you input, the more you're going to pay for using an LLM. When you're using an API, right, to interact with LLMs programmatically, you pay by the token. The vocabulary, these 100,000 words or tokens in the vocabulary, are optimized for the English language. And this means that if you input text in French, it will be split into more tokens because you won't have lots of common French. A few will be in there in the vocabulary, but most of French words will have to be split into smaller units, right? So it's going to actually be a bit more expensive to use an LLM in French than in English. And yeah, so that's kind of a walk through the token issue, the token situation. Any thoughts?
No, I was already aware of this one. I think it's good to kind of go over about. People always talk about like the tokens and the amount of tokens you can have, and I think now it seems like the average is like what, a million or a million and a half. Um, it sounds like a lot, but people kind of don't really understand that sometimes you do want it. Like you give an example in your book, if you want to like put a whole novel in there and ask it to summarize it or do whatever with it, it may not be enough. Like you said, hungry-ish is actually like two tokens together.
Yeah. Yeah, you're talking about the context window now, which is, it's not the number of tokens in the vocabulary, but the number of tokens you're inputting as a user in your prompt. And
Yes.
LLMs have a limit. There's a hard limit because the way they work is that they take the entire context at a time simultaneously up to a certain size, right? And now it's pretty big. You are, yeah, like I don't know the numbers, but you could be in the millions in some cases. But then if you input an entire book, it may not fit into the context window, which means that depending on the implementation, this may be rejected or the beginning may be ignored, for example. It will just be cropped out and only the the latter part will be considered. But this is very important for people also trying to use the RAG approach, which means that you go and search for relevant documents, let's say in a database of company information or private information of a business, and then you put all those documents into the prompt. Right? This happens secretly again. This is the idea of RAG, which is like I ask my internal in my company, I ask something about the company. Let's say you're a law firm and you want to know about a case, what happened with a certain case. So you type that information into the your chatbot window, and another separate system, this is not the LLM, another separate piece of software will go and search for documents in your database that are relevant to the question. This is done, again, separately using maybe some old school algorithm to match questions to topics or whatever, and then all this data is inserted into your prompt without you knowing it. So your prompt is enhanced with millions of tokens maybe, so that there is more information in the prompt to answer the question. But then there is a limit here, which is that if the context window of the LLM you're using is not big enough, then it's not going to fit in there. So yeah, we cover the context window now. Look, we're taking boxes here.
The $1.5 million is about the context window. I always thought that was about the amount of tokens you could have, but it like to evaluate. So that is the actual context window. So okay.
Yeah.
Gotcha.
Yeah.
All right.
So what happened, if you want to know a little bit of the history of this, before the transformer architecture was invented, which is this pivotal technique that led to ChatGPT, before that, the most popular way of generating text was LSTMs. That's the name of the previous technology. And the way LSTMs worked, they tried to fix this problem of variable input sizes, which happens a lot with text. With images, you can get away a lot easier with a fixed size. You can even resize an image so that it's always the same size before you give it to an AI to process. But with text, the length of text varies a lot depending on the input. And what LSTMs did was, again, they try to predict the next word, just like LLMs do. But the way they did this was they took the last word in your prompt, or the last token in your prompt, and all the previous tokens, they try to summarize the meaning of that into a handful of numbers, which is an embedding. We're going to get there. So every next word was predicted based on the current thing I'm looking at, the current last word, and a summary of everything I've said so far, which is pretty bad because it's essentially shrinking the entire context of the conversation into a handful of numbers, just to have a fixed size of the input that's given to this AI. And the problem here is that a lot of information was erased in this context. And the innovation of the transformer architecture was to read a very large context at once, all of it. And there's information about every token without compressing all this thing into a few numbers, right? So there's a lot more information that is not destroyed, before going into the LLM. That was the innovation of transformer architecture. The price to pay, though, is that the context window is kind of fixed, the size, right? You can go bigger. You actually typically don't even go smaller, in the sense that if your prompt is smaller, it's just padded probably with zeros. But anyway, this is the context window was, it's a good thing because before it was even worse. It was the entire context was squashed into a summary that was very, very rough. And that's why the LSTMs of that era, they were not very good at producing meaningful text, because they forgot the things that you'd mentioned because they were kind of compressed. And transformers fix that. Let me know if you have any questions, and then we can go to embeddings if you want.
No, I think the biggest questions I have is about embeddings, and then I'm trying to remember because it's a lot of information at once today. I was reading through it, and I believe there's also some recursion in there. Is that about the embeddings where you kind of start to I forgot. I have to go back and read it again. But you're doing this, so I'm guessing that must be correct in my remembering.
Yeah, so there are layers. Maybe that's what you're thinking about, the layers of embeddings.
Yeah, could be.
Yeah, so an embedding, let's speak of what an embedding is and why it's important. We said before we input tokens to an LLM. A token is essentially a word that we selected from a vocabulary of about 100,000 words. So essentially, I tell the LLM, this is word number 532 in the vocabulary. This is the input. Now, they're actually inputted as integers, right? So it's literally the index in the vocabulary. The question is that that's not meaningful. How do you telling you this is word 500 from a vocabulary doesn't mean anything? So one of the biggest challenges for the entire AI field, and when it comes to text analysis, is to represent the meanings of words or the meanings of tokens, right? And how do you represent a meaning mathematically, right? And that's called an embedding. An embedding is a vector of numbers. So it's essentially a list of numbers. Every token in the vocabulary is associated with an embedding, which is a list of numbers. And we can think of each cell in this list of numbers as a topic. It represents some sort of topic, like, is this an animal? And the number in that position tells you how much this is true. How much is this an animal, right? It could even have negative numbers, and you could think of that as this is the opposite of an animal. I don't know what that would be. But you can imagine one cell represents, is this a cat? And then the embedding for a dog would be kind of negative, because sometimes people would think a dog is kind of negative compared to a cat. It's the opposite of a cat. But then there will be another cell that will represent, is this a pet? And then both of them will have a high score. So essentially, an embedding is a list of numbers giving scores to different topics, right? And the first thing that an LLM does is map every input token to an embedding, right? The exact numbers in the embeddings are learned, right? Machine learning is used to fill those numbers in a sort of random guided search. Lots of things are tried, and an algorithm searches for a very long time. This takes a lot of energy, a lot of power to do. But essentially, this self-organizes, right? It learns from data what is a good embedding, how to represent meaning properly and in a useful way to predict the next word, which is what you're trying to do. Now, embeddings by themselves are not that great when you go and take a token and capture the meaning through an embedding. And the reason is that the meanings of words are different depending on the other words in the context, because words can have multiple meanings, right? You can think of, and I think in my book I give an example of, I wrote, the dog's bark is barely, and the LLM continued this with audible, right? But then I wrote the tree's bark is barely, and the LLM outputted visible, right? And this is because it understood that bark has been used in different senses, right? But that's not based on just seeing the word bark. It's based on seeing the word dog or the word tree in the context. So once you have these initial embeddings that represent the meaning of words, at least a preliminary meaning of words, what the LLM does, and this is where the heavy duty of the LLM comes in, it tries to create better embeddings by contextualizing them. So every token has an embedding, but now we'll use a little, if you want, neural network there that will try to analyze the meaning of, or the other embeddings that are present in the context window to try to alter the embedding of a word. So we can think of the meaning of words rubbing off onto each other, right? So if you have, the word, like I said before, I have the word dog, then that will kind of make the word bark more related to an animal, as opposed to the bark of a tree or a plant. So LLMs are contextualizing machines. That's what they do. That's what they were designed to do. And this is done in layers. So you have a first layer of all the embeddings talking to one another, let's say, to contextualize themselves. That's one step. And then that happens again on the improved embeddings. This happens many, many times. And at the very end, once these embeddings have talked to one another many, many times, you have really good embeddings that represent something very close to the true meaning of each token, right? So we can think of this pipeline where we first had tokens, which were indices from vocabulary, no meaning, and then we map them to an initial meaning, and then we refine and refine and refine the meaning using the context until at the very end, you have very, very meaningful information about the true meaning of this prompt, right? And that's when you can predict the next token, which is what the LLM does, very effectively, because you really understood the input very well. So that's the essence of how this whole thing works. What do you think?
Yeah, I think this is the part that really kind of didn't make a lot of sense for me. So I'm actually looking at, you have a diagram over here about the input tokens, your initial embeddings, which you talked about, and then finally contextualize embeddings. The contextualize embeddings part was a bit confusing for me on how that works. Is it basically just like, yeah, like with recursion where you can take this accumulator and then you just keep sticking it into this embedding algorithm kind of contextualizer? Is that
What it
what's
does, and
happening? Mm-hmm.
I think that's one of the parts in the book where I say, if you want to know more, you should go and I share a very good website. But essentially, it works like this. Let's say you're focusing on the last word of the prompt. You want to look at all the previous words, and the first step is to assign attention scores. This is called the attention mechanism, which is, imagine a pie chart, where you want to split attention, 100% of attention, among all the tokens in the context based on how relevant they are, right? So if you have the word dog, there will be certain words in the context that will be more relevant to understand the meaning of dog, for instance, compared to others, right? And there is an algorithm with a few very simple operations, which are mathematical matrix, multiplications and stuff like that, which try to convey the idea of searching for a certain key, like performing a query on certain topics or aspects of an embedding, right? You can imagine an embedding is a vector. You could multiply it by another vector, right, which has numbers, which are learnable parameters, to extract information about that embedding, right? You could calculate the dot product, which means you multiply numbers in the same position of the two vectors one by one, and then you add their results, and you get like one number that tells you how close is this embedding to what I'm searching for, right? Stuff like that. It's easier understood if you just go and see all the details. But essentially, it's like a sort of querying mechanism where you go and say, if a token is related to animals, it will produce a query vector that tries to find information about animals, right? And then this will be compared with all of the embeddings in the context by multiplying them with dot products. That's the most common operation here. And that's how you can kind of see where you should devote your attention. You just find the things that are relevant. And then once you've figured out the things that are relevant or the tokens that are relevant, another operation produces a new vector with information that is added onto the original vector. So essentially, let's say the word dog that is at the end of the context window, it decided that it should devote most of its attention to two words in the context. Then it will extract information for those two words that will be added onto the dog embedding. So kind of we borrow information and add it, right? It's all very simple mathematics, to be honest. It's nothing too complicated, but we're using matrices. What we try to do is we emulate this idea of searching for information and then combining information to refine an embedding, right? This is all inspired by observations of how we can disambiguate words using context. I don't know if this sheds any light on this without going into a whiteboard and going through all the details. But yeah, Is it at least a little bit clearer for you?
Yeah, definitely. And then at this embedding stage where you're going from initial to contextualize, is that where, like, at the end of that pipeline, is that where you start to do things like the temperature, where you can kind of do the fine tuning, or you do it? That's a totally different stage.
That's a totally different stage. So I'm going to write it down so I don't forget things. The temperature. Yeah, we definitely need to get to that. But yeah, essentially, the LLM, what it tries to do is assign a probability at the very end. So once you have all the embeddings, the context, what you want is a prediction of the most likely next token. But in reality, what is outputted is a probability of each token in the vocabulary of being the next one, right? So you have 100,000 outputs. If I say the Eiffel Tower is in, then the token Paris may get a score of like 99% probability, right? While other words that are totally unrelated will get very, very low probabilities, right? So you get a whole array of probabilities, and that's when the temperature comes in, because the LLM wrapper wants just one token, not 100,000 tokens with probabilities. So it will sample one of those words to attach it to the, when I say the LLM eats its own output, we need to select which output, right? And that's where the temperature comes in. Because when you sample, you can do it in a very conservative way, which would be to just pick the token with highest probability. If it says Paris, 99% probability, I mean, it could be the Eiffel Tower is in France, for example. So maybe it will be, 80% probability Paris, 10% probability France, another 2% Europe, right? So you could always go and pick the top one token and then attach it to the input. But something else you could do is use a very simple algorithm to use the probability values themselves to sample. So you're going to randomly select the token Paris with 90% probability, if the output was 90% probability. So we're essentially using the probabilities to sample. And you could use something called temperature to alter how aggressive we make this, right? If temperature is low, it means that we kind of push the probability of the top tokens a bit higher. So we're more conservative. If the temperature is high, we kind of equalize the probability of different tokens. We are more adventurous in selecting things that are not at the very top. So in practice, what this means is that the higher the temperature, the more adventurous the LLM or the LLM wrapper is at selecting tokens, right? And the more surprising the output may be, or the crazier the output will be. When the temperature is low, you mean you're making this very, very conservative. In some cases, with some LLMs, you may be able to pick always the top token without any randomness or any chances of selecting anything else. But that's the role of the temperature. And this is, again, at the very end when we use the LLM to produce one token and attach it to the prompt. Does that make sense?
Yeah, that makes sense.
Mm-hmm.
Yeah, I feel like we went through kind of the meat of that. I'm not sure if there's anything else in that frame that we didn't go through.
I don't know.
Is
There
it?
are lots of things to talk about, but yeah, I feel like that gives you an overview of how these LLMs work. In a nutshell, contextualizing machines, that was the key to this. It was, coming up with this attention mechanism, with this way of using a very rich context to produce an even richer context, because tokens have been contextualized, and then you produce the next word, and the temperature comes there to sample from that. But I feel like sometimes it's a bit underwhelming when you put it this way, because it's just predicting the next word, right? And what's very interesting about this, we need to talk about something else, which is how is this trained? How does the learning actually happen here?
That's actually what I
But
wanted to talk about too. So you talk about this is the deep learning and the machine learning, right?
yeah,
Okay.
exactly.
Sorry, go ahead.
Yeah. So do you want to go there next? Do you want to discuss a little bit how this is trained?
Yes, of course.
So from our previous discussion, we said there are those matrices where numbers are multiplied. There are lots of things that are parameters of this model. Parameters are just numbers inside of these vectors that are multiplied against the embeddings and all that. But essentially, the parameters configure the LLM, and they tell the LLM what it should do, right? And we can think of these as question marks in the program code that you write. And you can literally see this if you go to the source code, for instance, of GPT-2. You will see that they say, okay, we have a matrix of this size that will be multiplied with this other matrix. But the AI engineer doesn't define what a matrix contains, the numbers it contains, right? Which represent ultimately the operations, like, a dog being related to the word bark or stuff like that. So there's a phase afterward called learning, which happens actually in 2 steps. The second one's a little bit controversial. We're going to get to it. But the first step is to gather a lot of data from the internet, where you have trillions of examples of sentences and how they've been, what the next word is, because you can just hide the word. And you have an example. For example, you may collect a sentence that says the Eiffel Tower is in Paris, right? You can split in 2 and say this is an example of the Eiffel Tower is in, and then the word Paris. You have examples of how to continue sentences because you just gather all of that from the internet. And then what you're going to do is you're going to try to fill in all those blanks, all those question marks in the model. And that's what machine learning does. You start with completely random numbers. You have an LLM that does nothing of interest because it's filled in with random numbers that don't know the meanings of words. And you start kind of altering these numbers little by little. And you measure how much better the LLM got at the job of predicting the next word using that data that you collected from the internet, right? You can think of this process as going to a doctor's appointment for like an eye test, where they give you a prescription and they tell you, do you see better than before or not? And they alter the prescription a little bit, and then they ask you again. And it's the same process, but on steroids, right? It's done millions of times, and it takes a lot of power and lots of GPUs and machines. But essentially what you do is you take the LLM, you alter the parameters a little bit, and you see if it gets better or not at guessing the next word based on all that data you collected from the internet. And this is very powerful because guessing the next word overlaps producing true statements and solving problems. They overlap. They're not the same, but they overlap. For example, a lot of people ask questions about coding online, right? And the best guess of the next word is to kind of, for the LLMs to mimic the answers that you find in the on the internet, right? So this idea that seems a little bit simple of predicting the next word is actually very powerful, because sometimes, predicting the next word means you need to solve the problem correctly. So essentially, the first version of the LLM is created by gathering a lot of data, pretty much all the internet that's publicly available, including illegal stuff, including pirated books, things without authorization. That's the way they did it. And they gather a huge database of text. And then the LLM, or the training algorithm will try to produce an LLM that is great at guessing the next word in that database. All a bit of like a trial and error, like the doctor's appointment, like we said. And that's kind of concludes the first stage of the training process for the LLM. That was only half of the story, though. And we're going to talk about the second half in a second, the controversial one. But tell me what you think about this, or if you have any questions.
No, I got this one. It makes sense. I mean, of course, we're going to get more into like the unsupervised, and I know it's pretty interesting too that there's some people that you can actually like. Yeah, that I like also how you talk about how you can also use LLMs to generate data, and also that you shouldn't use it. It's like there's an example you give about people using an LLM to, or using an LLM to like, or I don't know if it's an LLM or not, but using some kind of learning to create this model that can actually play Go, and they actually use generated from LLM, I guess it was, or some kind of model to generate the
That
content?
that that wasn't an LLM, but it was another type of AI. And this is very important, actually, the point that you're bringing, because like you just saw, LLMs learn from gathering a huge amount of data from the internet. This data, some people would call it unsupervised, meaning that there wasn't a human actually telling the LLM, look, this is what you should output here, right? But in reality, it was created by humans, right? So this because they wrote that data, right? Which is going to get tricky because the day the internet is flooded with text produced by AI, it can't really learn anything new from its own text, right? There's no new information. And there's sometimes a fantasy going around that you don't need humans, you can just simulate data. And a lot of this myth, if you want, came from the algorithm or the AI that learned how to play the game of Go, which was very famous. It was a breakthrough in AI. I think it was maybe 2015, 16. It was about 10 years ago. And there was a paper that they published saying that Go learned without human knowledge, or like the AI learned how to play Go without human knowledge. But that wasn't really true. So what they did was they took a machine that played against itself to record lots of games, simulated games. So there was no human knowledge in terms of real games played by people. They were all simulated games. But then there was a lot of human knowledge involved in designing the solution for this, right? And also this idea of generating a lot of simulated data, it can work in very restricted contexts like game playing, which is very algorithmic if you want. But you can't generate simulated data of general text, what people would have said, right? Because if you could do that, you already solve the problem, right? You don't even need to learn anything. You already know what humans say. You're trying to learn what humans say. So you actually need humans to speak and say stuff. And then you learn from that data. But yeah, this is something that I've come across a lot. People thinking of, because we're pretty much running out of data now for AI to learn, right? So they've used the entire internet. So there's no more public data pretty much for LLMs to learn from. So what's next? And some people say, well, just simulate data. Well, that's not going to work because what algorithm are you going to use to simulate data that isn't just replicating what we already have? You can't really do that. If you could, you would have solved the problem already, because if you had an algorithm that can simulate proper text, then you already have your LLM, essentially. You can see this pretty clearly with translation. Translation is usually so AI for translation learns from documents that have been translated by people. Usually, for example, at the EU Parliament, or the EU Commission, you have lots of documents that are written in 2 languages, 3, 4. In Canada, you have a lot of things written in French and English, right, in parallel, and AI can learn from that. But can you generate simulated correct translations for AI to learn from? Well, if you could do that, then you already solved the translation problem, because you already can generate correct translations. So essentially, it's like a bit of a chicken and egg problem here. So yeah, what I'm trying to say is LLMs learn from data produced by humans, and there's no amount of simulation that will solve that. We need people to say things for the LLMs to learn. Except restricted, problems like game playing or very algorithmic things where you can generate simulated data. But yeah, that's the first phase of learning. Any questions?
My big question is that, I mean, obviously as a programmer, I understand how I can write algorithms and things like that, but how does this thing uh, work under the hood in terms of, like, because you have something coming in, let's say the supervised one, you have, here's the input, here's the output, it has to match. Is it writing to a database somewhere about how to make a choice? Like, how does that part kind of work? Because it's trained and it has to somehow save the methodology of how it works. Now, like, this part I never really understood when I hear about training a model, because I'm used to source code. You compile it, it doesn't change, but this one does. So how does that part kind of work?
So essentially, what you do is you create a database of examples with the input and the output you would like, the output you would expect from the LLM. This is literally a database. People tend to call it a data set in the industry. But it's essentially a database of examples. You can think of X, Y pairs. The X is the Eiffel Tower is in, and the Y is Paris, which is that's what I want you, the LLM, to output. You have 1 trillion examples. What you can do now is give your LLM, this is what literally each iteration of the algorithm, the learning algorithm, does. You give your X inputs, so 1 trillion X's, to the LLM. The LLM produces 1 trillion predictions, so the Y's. Now you compare the two. You compare the Y produced by the LLM with the Y you want. In some cases, the LLM will output the correct word. For example, it will say Paris when you wanted Paris. In other cases, it won't. It will output, hello when you wanted Paris. And what you do is you calculate a score that measures the error. This is called the cost function or the objective function that says how bad or how far off the LLM is from producing the result you want. And then, and this is where calculus comes into this picture, you vary the parameters of the LLM, all these internal numbers that define the behavior of the LLM, you vary them a little bit, only a little bit locally, to see if this measure of the error changes. Imagine you randomly tweak a couple of parameters a little, and then a word that wasn't predicted correctly is now predicted correctly. It's what you wanted. Then that's a success. And what you're going to do in this iteration is you will update the parameters in that direction a little bit. So it's literally moving the numbers around so that locally you can, with minor changes, you can move in the direction of improving your performance on this data set. It sounds, I don't know if that was clear, but if it sounds a bit crazy, because it's insane, you're just like tweaking things and seeing what happens. If that sounds a bit crazy, well, it is crazy, and that's how it works. It's in the beginning, it's a needle in a haystack. You start from scratch, and you little by little start finding improvements. You're like, if I change these parameters a little bit, then in the beginning, maybe just a couple of words, and your entire trillion words that you have will be predicted correctly thanks to the tweaks. But over time, after doing this for a very, very long time, you will end up with an LLM that is good at producing the predictions that you want according to the data in the examples that you gave it. Does this make any sense?
Yeah, that makes more sense now.
Yeah, let me tell you about the first stage of this learning process. Is all based on data collected from the internet, which means that sometimes it will be inappropriate, and the providers of AI didn't like this, but also sometimes it will not solve the problem correctly, because this is trained to produce the next word, not necessarily to solve a problem correctly. So sometimes it will output something that sounds great, but it's not the right solution to the problem. And the way to solve this is called reinforcement learning with human feedback, right? The way it works is as follows. They create a lot of outputs using an LLM, sometimes alternative outputs. They produce 2 different outputs for a possible input, and they ask humans to label them based on what they think is a correct, appropriate, effective output or whatever. So they literally have people, some people say they've hired people in Kenya for $2 an hour to do this, but you literally have people looking at thousands of outputs and ranking them and saying this is good, this is bad. So we go to actual human work to refine the LLM, right? And then all of this information is used to train another machine learning model that will try to predict the quality of an output. And then this is kind of fed back into the original LLM to improve it and align it to the outputs that these humans would like to see. But essentially, the second phase of training is much more related to what people want, and they specifically created data manually, examples that were created manually. So it's no longer just collecting data from the internet. And this is so that we kind of imagine a little bit more what's going on behind the scenes. When they train those LLMs, there's this less elegant phase at the end where they literally hire people to correct the LLM, if you want to say this is inappropriate, I don't want this output, and then try to refine the LLM based on this. And this is the second phase of the training of the LLMs that we find available, commercially by OpenAI or Gemini. There's definitely a human component, right? Because just learning from the internet did not work the way they wanted. I'm sorry if that's disappointing.
No, I mean that definitely makes sense. I also just remembering back to what you're talking about, like if you can generate the translation, then you don't really need to train a model because you can do it already. So it's a pretty good
Exactly.
point.
Yeah. They couldn't generate appropriate text from the internet that contains a lot of inappropriate stuff, right? They couldn't.
Yeah.
So they had to actually hire people to manually write examples of or create a database, an additional database, if you want, of training data that says this is an appropriate output, this is an inappropriate output. And they fed that back into the LLM to refine it.
Is this what you're talking about? Like, I remember you had this very interesting phrase. It was like, but maybe this is not the same thing. But I remember you were talking about like best and not best, which sounds kind of strange when I read it. It was one of like the what was it? Let me go back to this section. Do you remember? This is about.
Let's see. I write a lot of things, so we need to see what.
Yeah. This was related to the reinforcement learning. So it's actually like, what do you call that? What would be the best way to say it? Like extending or like, yeah, just reinforcing the model, right?
Yeah. You can think of this as it's a reward model. So essentially, you try to. It's like when you train a dog, like good boy, bad boy. It's a little bit like that. Yeah. You get humans to label sentences or produced by the LLM outputs into kind of appropriate, inappropriate, or good, bad, and then that is this reinforcement learning. That's the technique that is used to use that and try to get the LLM to become more appropriate.
Okay. I mean, we've gone through quite a lot of detail. I feel like if we keep going, you're just not going to sell a single copy, which I think you should. I think this is something that people need to get in there and read about it. Kind of coming back to it. Let's try to like kind of wrap this up because we'll be here all day if we start talking more to the details. I'd like to discuss like more about what is like the core of this book, like what's it for. I know we kind of talked about before, but more kind of like pillars of what's actually in the book. And I guess unless there's anything else that you wanted to say about it, but I think that's actually a good point to start to end it.
Yeah, look, I've been for a long time, fighting against this hype around AI because I feel like we need to acknowledge the limitations of AI, and the people who will succeed in this field are the ones who acknowledge the limitations. I've spoken with startups that acknowledge from the get-go that hallucinations are a problem with AI. When AI outputs something that is horribly wrong, but is very confident about it. And that's going to keep happening. Nobody knows how to fix this. And that should be clear from a conversation earlier. Like these are, machines to predict the next word. They're not designed to output the truth. So hallucinations will continue to take place. If you design your product around the hallucination, so for example, you provide help to a user that they can use or not use, then you may succeed. If you produce a product that promises I'm going to do it for you, you will never need a human because the outputs will be perfect, you'll be in trouble because your AI will not be able to fulfill that promise. So in the remainder of the book, I touch on a lot of these things. What are hallucinations? Why do they happen? How can we mitigate them? Will they stop? And then I cover a lot of the other fine print of AI. For example, what's the crux of the issue with the copyright debate? Like we said before, a lot of data used to train AI was harvested from the internet without authorization. So, what is going to be the most important topic in the legal debate, around that? So I just, the book covers lots of those things that are important to know to build a successful product, to understand in general the industry. I also explain things like, when to use AI and when not to use AI. There are some cases where it's best not to use AI and do something else. There's a catalog of tools. There are classifications of AI. So what's the difference between a foundation AI model and an AI app, for example, and stuff like that? What is open source AI? What is proprietary AI? What is fine tuning? What's a RAG? How is that different from fine tuning? So all those questions that will help you kind of navigate this industry. I hope the book will answer those. That's what the rest of the book is about. So we have a first chapter, which is what we talked about today. How do LLMs work, and also other types of AI. But what is AI? What's happening? And then we move on to other important topics to work in this field. Like I said, copyright, like when to use AI, what is fine tuning, all that kind of stuff. So we move on to less technical and more practical kind of topics.
Okay. No, that's a great book. Again, I highly recommend this book. If you're going to pick it up, definitely go to Manning.com and buy it, because a bigger cut will come to you. I don't think Jeff Bezos needs another trip to another planet. I don't know where the heck he's going these days. So definitely pick it up from Manning. It's a great copy. We'll probably have a discount code in the show notes. Yeah, I mean, other than that, I mean, again, I'll just give you a last chance if there's any kind of last words you want to give before we head off.
Yeah, look, I think it's, the AI industry is very seductive. It's very fun, to work using this amazing sci-fi like technology. But I would tell technology professionals to remember that they work for users or for customers. So the first thing you need to do is try to understand what your customers need. Because at the end of the day, I feel like that's the most fun thing to do when you serve a client. And sometimes that's not AI. You believe in the beginning that you need fancy AI to do something. And then actually your client needs something else that's simpler, but will do the job and will make them happier. So let's not forget that engineers are meant to find the best solution to a problem, right? Not to just choose the solution first, which is AI, and then try to use it everywhere. So just remember about customers, users, their needs, and try to help them. And AI is a tool in the toolbox, but there are other tools.
I think that's a good point. I mean, too many people are just trying to throw AI into everything, and sometimes it just doesn't really make sense, at least not to me. And yeah, I actually came from a company, and they were just like trying to figure out how to put AI into something. It's like, but what do you want to do? What do you want to do? You can't just use the buzzword AI and then just ask
that's
me
the story
to
of my
do it.
life.
Yeah, exactly. So tired of
I've
that.
seen it. Yeah, I've seen companies create a department that just tries to promote using AI within the organization. And I don't think that ever ends well, because at the end of the day, they're just trying to push AI because that's also the job that they have. And instead of trying to understand people, they're trying to prove very roughly that, you should use AI for this, do this, and it wasn't great. I've seen it from the inside, and it's not great. Yeah.
Yeah, definitely. Yeah, okay. Again, pick it up from Manning.com. We'll probably have a discount code in the bottom of the show notes. Great to have you on, Emmanuel. I'm looking forward to picking up your book once my thing recycles, because I have no idea what I'm going to listen to next. So I think this is a great chance for me. And because I like this book, I'm guessing it's going to be another great book to listen to. So looking forward to
Hopefully
it.
you like it. Yeah. Well, thank you for having me. Thank you for your interest.
And thank you. Yeah, thank you again for coming on.